Thank you. Well, good morning. It's a real pleasure to be here, honor and a privilege to talk to such a remarkable assemblage, and it's a special pleasure to be out of Texas in July. So last night, I was like, I should have brought a warmer coat. Wonderful. So today I want to try and get through some of this stuff, and I hope to be interrupted frequently. Don't throw any rotten tomatoes. I hope that it elicits some concern for my sanity, but I think that you'll find some of these discussion items interesting. What is plate tectonics? I mean, basically we all know what it is, but let's talk a little bit more about it, because as we go through the question of what makes the plates move, this issue of what plate tectonics is, it becomes important. And then we do have to address this issue. We sort of are uniformitarianized into thinking that what's going on today is common and expected. The present is the key to the past. If we understand our planet, we understand other planets. But I think this question, is plate tectonics common or unusual, is critical for understanding the history of our planet. And then we do need to discuss a little bit about, okay, who cares? So what, when plate tectonics began? It really does turn out to be very important in terms of understanding continental crust, to understand, first of all, when the processes that are now building it, and as you'll see, destroying it, started happening. And then we do need to talk a little bit about how planets cool, and then this is a particularly good place to talk about the Urey ratio, since Harold Urey got his PhD in chemistry here almost 100 years ago. And then finally, if we have time, we can wander through what I think are important petrotectonic indicators of plate tectonics. I think each of us has an opportunity to say what we think are the important hallmarks of plate tectonics, and start that discussion. So without further ado, and with the full expectation that you'll interrupt me without raising your hand, and Cinti will have to run around, or Richard's going to have to run around with the microphone, just chime in. I may get halfway through this talk. Maybe we'll get lucky or unlucky and get through the whole thing. So let's talk first about what is plate tectonics. Just to remind you, Earth has 11 large plates and many more small plates. And those of us that are interested in the continents sort of have to put plate tectonics in a separate box, because most of the areas where the plate tectonic approximation doesn't work are on the continents. This has got to do with the rheology of continental crust as opposed to oceanic lithosphere. But anyway, where we have plates, they are basically a code word for lithosphere. Lithosphere plates, these are exactly the same thing. And it's one of the problems I have in teaching tectonics to undergraduates and graduate students, is they tend to equate the plate to the crust, and that's wrong. The plate is the crust plus the uppermost part of the mantle. Plates are typically 100 to 200 kilometers thick, depending on how you define them mechanically, thermally, whatever, up to many thousands of kilometers across, and they're moving at speeds, that are fortunately we can relate to, centimeter to 10 centimeters a year. That's how fast our expendable body parts, nails and hair, grow. Some of us, it's more expendable than others. So these are the fundamental features of plate tectonics. We have destructive plate boundaries and constructive or divergent plate boundaries, mid-ocean ridge spreading centers, subduction zones, and then sort of second-order features like transform faults, which probably isn't going to be second-order when this one fires off. But in the grand scheme of things, this is where the action is, the spreading ridges and the subduction zones. And this is an old representation of the plate approximation, and it's a pretty good one. But what you notice is this flow of the asthenospheric mantle is just the opposite of what we often see. That direction of flow is one of the most important things that we really need to resolve. So these are the top 14 plates in area. The Pacific, by far, the largest and getting smaller all the time. North America keeping up there, Eurasia, Africa, down the list. top 14, down to the little Cocos plate, and then many others ranging down in a fractal down to your microplates or whatever. So one of the most important characteristics or definitions of plate tectonics is this geometric approximation that we can describe plate motions by motion around an Euler pole, that the relative motions between the two plates is defined by this angular separation around a pole of rotation. And there's different methods for determining the Euler pole, transforms, earthquakes, all sorts of things. And this is our modern understanding of the major plates' relative motion. What I want to draw your attention to is not the plates, because they behave so well, but these areas in the continents where plate tectonics kind of goes out the windows, where you have broad zones of deformation that the plate tectonic representation is almost meaningless. What's the plate boundary between India and Eurasia? That's a fool's game, really, because it's all of this strain is distributed all through basically China and many other places, the East African Rift, the Andes and the Western Cordillera. When you're on the continents, you're not as interested in plate tectonics as you are if you're in the oceans, and it's not really a surprise that plate tectonics came out of marine geology more than continental geology. So we've got a really good understanding of how the plates move and where the plate tectonic approximation fails us, and that's a very useful thing. But where we're struggling, and maybe we don't appreciate what we don't understand, is the difference between kinematics and dynamics. So kinematics is a very simple description of the motion, and in plate tectonics, that was the great breakthrough, was that the plates, that the Earth's lithosphere was broken up into a number of plates, and the motion of these plates could be described. And it was an amazing thing that happened in the late 60s and early 70s that we were able to do that. But what we left sort of in the dust was understanding what caused the plates to move. So we celebrated our success in a kinematic description, just describing what motion, and maybe we didn't do as good of a job with the dynamics. That's where the real future opportunities, I think, are, is coming up with dynamic interpretations. So just to make it more intuitive, I like that word, talking about making things intuitive. The kinematic description of a car's motion would center on the direction, speed, and maybe in a little bit of detail you'd say, well, let's talk about what the tires are doing. Those would be kinematic descriptions, and a dynamic description of a car's motion would maybe also discuss gasoline, engine mechanics, thermodynamics, transmission, wind resistance, things like that. Not to degrade kinematics, but dynamics is a different kind of understanding and perhaps a more useful understanding of the way things operate, if we can get there. So we've got a number of very powerful kinematic models for the plates. It's been a remarkable demonstration of plate tectonics. With the development of satellite geodesy, we are able to check what we came up with in terms of plate motions based on magnetic anomalies and Euler poles and all of the things that we were limited to in the 1960s, 1970s, and 80s. And then with this huge breakthrough in satellite geodesy, we were able to go back and say, now, let's see if that was right. And the plate tectonic approximation is remarkably consistent between these geologic indicators of plate motions and the geodetic indicators of plate motions for the larger plates. The smaller the plates, the less things agree. But these are some of the sort of standards. Nouvelle 1A, these are geologic models of kinematics, and the more recent version of this is called Morvell. I don't even remember what that acronym stands for, modern relative velocities or something. But these are based on seafloor magnetics, transform orientations, earthquake slip vectors, and are useful for back 3 million years or so. And in contrast, the geodetic ones, beginning with Revel and the most recent one, GeoDevel, I'm not even sure how to pronounce that. These are nearly instantaneous plate motion from GPS. Good for the last, well, mostly GPS, other kinds of satellite geodesy. Only good for a few decades. But these are both remarkably consistent for the large plates, remarkably, it's very confusing when we start using these different techniques to understand what's going on in the zones of continental deformation. But this is a nice summary. Plate kinematic models, the geologic models are with the yellow arrows, and the satellite geodesy are with the purple arrows. A little bit hard to see the purple, but for the most part they agree, except for the smaller plates.
So can I
yeah.
So when you said these two, the geodetic and the geological plate motion model agree with each other for large plates, the small ones, what are the plates that don't agree?
Well, the most spectacular, I would guess, would be the Tonga Kermadec. What's the name of that plate? Doug, do you remember what you call that? Is it the Lao Basin plate? The Tonga, the thing that's on the east side of the multiple spreading centers of the Lao Basin. That was moved with geologic. It was argued to move much more slowly, and now with GPS, we can see it's.
I mean, the reason that I ask this question is I can see the geodetic ones may differ from the geological ones due to process like post-glacial rebound, for example. And that actually kind of will cause some modern deviations from the geological.
Probably.
So I guess it's more like whether the place like Antarctic, there you may actually see more influence from the rebound.
I don't think rebound's a big part of the inconsistency, because that's vertical, and I think when these models are nearly all horizontal motions. By and large, these models for plate motions are purely horizontal. But Doug, maybe you have some.
I mean, it is true maybe that in Antarctica, where you're looking for something very subtle, like the difference in velocity between east and west Antarctica, which is certainly well less than, like, say, a half centimeter a year, the post-glacial rebound signals become important. So if you look at a horizontal velocity map from GPS across Antarctica, it's really wild. Because you have a lot of local effects of post-glacial rebound. But that's at the very slow, much less than a half centimeter a year level.
Yeah.
But there must be also some averaging over earthquakes, right? I mean, these motions along plates aren't smooth and uniform.
Do we have a geodetic plate measure expert in the audience? I'm not that person, but I mean, this is a hugely vigorous field in our science. And these details, what I consider details in terms of the plate scale, what's happening vertically with post-glacial rebound over the earthquake cycle. These are huge concerns for things like the Plate Boundary Observatory.
So in some ways, it's a little surprising they agree that well.
Yeah, I mean it is we don't get very many kudos from ourselves very often, but I think as a community we should congratulate ourselves on doing a pretty good job. We had no idea GPS was going to come along and test all of our models, and it's a remarkable demonstration of the strength of those arguments that happened 40, 50 years ago. Yeah.
I guess just to know that some people have argued that it used the degree of mismatch to say something about a change in plate motions over the last, say, half a year. Well, this is a model that. So, there's some second order agreement, and you have models for, discrepancies in constellation discrepancies.
Yeah. So there's even signal in the noise. Doug, you had another comment?
I was going to say I'm not really an expert in this area, but early on when GPS first started, people were interested or wondering whether there's any temporal changes, as you get sort of towards the center of plates.
Yeah. I mean, what I take from this, not being an expert in either the geologic or the geodetic measurements of plate motion, is that there's not a lot of controversy. There's a lot of information in these issues of glacial rebound, the earthquake cycle, whether the plate approximation works. And my sense is that for the most part, the two large-scale information sources are remarkably consistent. Okay, so we're kind of in a little bit of the position of the Native Americans when they first saw a steam locomotive coming across. It's like, okay, what the hell is that? And the first thing they developed, or any culture that was unassociated with, unfamiliar with any technology would have been able to figure out, would be the kinematics. How fast these things went. A number of issues about what the relationship between the wheels and the motion was. But the dynamics of a steam engine would have been something quite different. There would have been almost no way until they were trained in what a steam locomotive was, how heating in here drove steam, and how the steam drove the cylinder, and how the cylinder drove the wheels. Those dynamics, that's kind of where we are in a way with plate tectonics. We're sort of in the same position as the Native Americans were in facing the iron horse. Kinematically, okay, we can figure that out. Dynamically, that's going to take us a little while. So we have these kinds of things. We teach them. Most introductory geology texts show them, and what they say, and when the students naturally ask, why do the plates move? The answer is mantle convection. So here we can see an interpretation. There's a million of these. I'm not picking on any one. I'm sort of picking on our general ignorance about what makes the plates move. You see this, and you notice the direction of the asthenosphere is quite opposite the one that Isaac showed originally. But it's this huge thing circulating from the core to the surface that makes the plates move. That's really a tautology, because what plates are is part of the convection. So in a way, if you ask what makes the plates move and answer mantle convection, you're saying what makes the upper part of the convection cell move. The answer is the convection cell makes the upper part of the convection cell move. Okay, maybe you can get away with that with a group of undergraduates, but I don't think we can get away with this understanding. It's a tautology. A tautology is something very useful to recognize when the main evidence that you're making for your argument is your argument. And that's what the statement that the plates move because of mantle convection is. It's a tautology. Okay, so let's talk a little bit about our understanding of what makes the plates move, because we can't really understand the history of plate tectonics on this planet unless we have an understanding of what are the forces that make the plates move today. Because fundamentally the question of when did plate tectonics begin is a question, when did the forces that drive plate tectonics first become powerful enough to overcome the resistance of the lithosphere and start subduction or spreading or whatever causes it. Okay, so this is a summary from a really classic paper by Forsyth and Ojeda in 1975. They're almost up to 1,000 citations, but they're still being cited. It's one of these papers that's still keeps providing insights and motivation for studies. But they basically tried to summarize all of the forces that were involved in plate tectonics. Ridge push, we talked a little bit about that with Claudio. Maybe you could lump in plume push into the ridge push force. This negative buoyancy force, the sinking of the slab in subduction zones. Slab pull, which is the way they've shown it, is transmitted from something going on down here to what's going on in the plate. Trench suction, which is a mysterious force. And then the resistances, the ridge resistance, the bending resistance, the fact that it takes a tremendous amount of energy to bend the thick lithosphere, the slab resistance, the fact that the slab has to penetrate viscous mantle, the overriding plate resistance, the mantle drag under the ocean, and they distinguish it from the mantle drag under the continents, which is a theme we'll probably return to, that the plates seem to experience different resistances depending on whether they're in the oceanic realm or the continental realm. And these mantle drag forces, both for the ocean or the continent underneath them, can be either positive or negative. We saw that with the two cartoons, the one of Isaacs and the one of the whole mantle convection. You know, you can have the mantle flowing either way. You can make strong arguments. So let's see if we can put this into a nutshell rather than spend too much time on this really interesting problem, and talk about the two main things, which are ridge push and slab pull. And Claudio, yesterday at the end of the day, put this in a very nice synopsis, you know, these tensions between, okay, what do you think is more important, ridge push or plume push, which is an interesting variation, versus slab pull. And so people have modeled ridge push in a number of ways. It's as a body force and as a boundary force. So as a body force, it's attributed to the cooling and thickening of the oceanic lithosphere with age. So the fact that the ridges are higher and they're made of rock and they want to move down. We see this over and over again in terms of what's happening with orogens. The Himalayas can probably only get to a Tibetan plateau, can only get to a certain elevation because of the body forces that are making it want to collapse. Ridge push as a boundary force is the idea that there's something that's forcing its way up into that region between the plates and sort of elbowing its way in there. So that causes a sort of a horizontal pressure gradient. So anyway, Forsyth and Yeda and other people have come in and tried to quantify that. So the ridge push force, very simply, is just rho GH minus the rho G of the water overlying it. And you can simplify it just to get a sort of a order of magnitude number, which is on the order of 4 times 10 to the 12 newtons per meter. So what we can do is do the same thing with a slab pull. And this is the sinking of the lithosphere in a subduction zone. And this is basically reflecting the fact that the density of the lithosphere, because of the coefficient of thermal expansion for mantle peridotite, is thought to be about 1% higher than the asthenospheric mantle. So that small difference provides a body force for the lithosphere to sink into the mantle. And we argue about, you know, what is the real change and difference in density between the lithosphere in the subduction zone versus the ambient mantle. You know, what does eclogite do when you convert into eclogite? What does that add to it? But in general, the slab pull force depends on the dip of the subducted slab, the length of it, the age of the subducted slab. You know, younger oceanic lithosphere is much less, has a much, somewhat lower delta rho than old oceanic lithosphere, and the temperature difference between the slab and mantle, which controls the coefficient of thermal expansion and the density differences. So with estimates, you can do the same sort of thing, the body force that you get with a slab pull, and you can do that. And they come up with something on the order of 5 times 10 to the 13th. Other people have calculated it 3 to 5 times 10 to the 13th newtons per meter. But what you see is that the ridge push force is an order of magnitude smaller, according to just about anybody's calculation, than the slab pull force. And at the present understanding of what's making the plates move, it's the sinking of the lithosphere in subduction zones that drives the plates. And this is a point that I understand there is some controversy, and I invite the junior Siderites to stake out your own position, examine this. Don't take my word for it. But this is basically my understanding of what the bulk of the geodynamic community has to say about what drives the plates. And I really invite the senior Siderites to comment on this, because if I'm leading anyone astray, this is the time to set me straight. Okay? Yeah?
You haven't said anything about the other thought, the traction part. You've just compared the ridge push to the slab pull.
Yes.
So, do you want to say a little bit about that, maybe?
I think I'd rather you said something about it. Because I really, what I saw in those cartoons and is that Isaacs and Alvarez show the asthenosphere moving towards the ridge, away from the plate. And what I see other people showing is that they have the asthenosphere moving the other way. So the first question I would have is, which way is the asthenosphere moving? Alvarez, I think, made a fantastic argument that as the Pacific shrinks, the asthenosphere is getting squeezed, and it finds a way out in the South Scotia Arc, and it finds a way out in the Antarctic, Australian discontinuity, and maybe out through the Caribbean. It's sort of moving in neither one of these directions. But the traction force resulting from whichever way the asthenosphere is moving, I really am uncomfortable saying much to anybody other than this is confusing and it doesn't seem to be important. Would you agree with that?
I don't have a particular opinion. I guess what I was getting at is you try to estimate the magnitude of the forces, and how do we have any possibility of coming up with a similar estimate of the magnitude of the forces for the traction? I think the answer is no. I don't know.
I guess the forces balance. They should be equal.
What's that?
The forces are all balanced, right? So if you know the driving force, then you must have resistant force to balance it out.
Yes, but I think the question is in this simple-minded description of what's driving the plates, have I left out an important point, which is the traction force? So for people that aren't familiar, the idea is that there may be a force acting on the bottom of the plates, and in fact, we think there is, because if you have a continent on a plate, that plate is going to move more slowly than if you don't. This is one of the observations. And it's not too surprising, because continents have these thick keels, and so they extend down into the more viscous part of the asthenosphere, or maybe below the asthenosphere, and they move more slowly than oceanic plates, which have thinner lithospheric keels.
Bob,
Yeah.
I've heard just the opposite.
Okay.
The up-down sailboat model. The continents have these keels, they catch the convective forces, and it pushes them along faster. That's not observed.
No, it's not observed. You might think that one observation would be, okay, if there is a mantle wind, and people have argued there is an asthenospheric wind, that you might catch it with what you said, an upside down sailboat, but.
And of course, several years ago, that if you look today, you would have the impression that plates with continents move slowly, but he argued using past motions that this was probably just a snapshot, and that when you look over time, there's no systematic dependence between the continents and the velocity. That's not studied at the same time as force as you did.
Mm-hmm. So, yeah, get some questions over here.
Yeah, I guess, the same way that you said at the beginning that we can't just say, well, the plates are part of the convection system, can we really totally isolate the plates and do a force balance on the plates without considering the rest of the convective system? Is it too simplistic to just say, here I have my plate and what's pushing what direction, and not consider the whole rest of the system?
Well, I can't answer that question, except that success in science often goes with the ability to reduce a problem to its simplest parts. And if you want to make a big name, answer the question for all the plates. But if you want to make a name, doing it for one would be a good step in the right direction.
I'm not really talking about all the plates. I'm talking about the fact that you have an entire convective system and not just the little thin, lithosphere at the top. I mean, I think you do have the largest driving stresses associated with the places that have the largest temperature differences, and which would be the plate. But still, it seems like you're neglecting the rest of what's going on.
So, Claudia.
Just a comment on that. It is being our first for a student to appear in the situation. There's been a lot of work done on the topic. If there is a slab pool or slab suction, where more important, the slab suction is the drag of the mantle, the drag in there, and how the lithosphere participate, as Doug saying, to the convection system. So, for example, from the O'Connor paper, like we're talking about 40 years ago, and I think, for example, an interesting paper that students can look at is the paper by Conrad and Carolina Bertoloni, where they try to give percentage of the importance of slab pool versus slab suction, looking at the kinematics of the upper plate and kinematics of the ongoing plate. This is paper published in Science in 2002. And I think he gave an overview of the problem. And that is, of course, they come out with numbers saying that, for example, some can be 40%, slab suction 60%. That is to say that it's difficult to discriminate where is one of the others, and Adrian was pointing out that, and also after our discussion. And it's clear a combined issue. So in some places you can have another one aspect is more relevant, and some other aspects are more relevant. And it's room for work.
No, and I think that as this discussion has shown, there's a tremendous interest in understanding in greater detail what makes the plates move. So my issue here was back.
I was just going to ask if you could put that on the wiki, that paper. Pardon? Could you put that on the wiki?
Yeah, sure.
Another way to think about this is think about convection from an energetic point of view. There's sort of two issues. Either you've got cold stuff going down, or you've got warm stuff coming up. And what we think about the sort of heat fluxes through the mantle, it's probably mostly the cold stuff going down rather than the hot stuff coming up. So that really leaves you two options. Either the cold stuff, which are the plates, are driving the motions by the stresses that get transmitted through the plates, or they're driving the plates through the large-scale circulation that the sinking motion is actually driving. It has to be one or the other, and probably a bit of both.
And there was another,
Well, I guess I just want to add to that. I guess one way I look at it is it's kind of helpful for myself, but I'm not sure it's going to be useful for the rest of the audience. That is also just by looking at the energy. So we know the mantle convection heat flux is about 36 terawatts, and then you can actually just take the plane motion that we have, and you estimate the sort of the energy flux associated with the downgoing slabs. You actually see that the downgoing slabs really accounts for about 80% of the surface heat flux. So that, to me, that is actually very good evidence that the convection, or the plane motion is largely driven by the plates, sinking slabs, not the other way around. So I guess we've been hearing this top-down tectonics or bottom-up tectonics. I cannot envision how this sort of bottom-up tectonics can ever work. So I think this is what I guess what I'm saying. I actually agree with what you summarized. I think that we shouldn't really confuse ourselves by bringing all this kind of various forces. They're probably there, but probably not very important.
question? Kent?
Yeah, I think this problem you brought up, which way the asthenosphere is moving, is very important. Nobody here has addressed it yet. I'm wondering, do we have an answer to that? Something's wrong. Our geology, beginning geology textbooks, just like you point out, some of them show it going one way, some of them show it going the other.
They went that way.
It's not that question. Does anybody know?
No, I think there is a community that actually has considered this in detail, and maybe this is part of the problem of keeping up with the literature, which the junior Siderites, I think, will appreciate this, that this expert discussion has happened, and we really wish they would come in and explain it to us in a way we would be able to put into the introductory textbooks, or make the argument, hey, you guys need to stop reusing those old figures, just adding color to them, and update them with some of our modern science.
So I gather we don't have an answer to that question because nobody's giving it.
No, we do, but let's hold this off, and I think we can have a discussion about this over coffee. But you had a...
I'll just very quickly say that, I mean, one of the observables that we have that can tell us about shear at the base of the lithosphere is seismic anisotropy.
Mm-hmm.
We'll talk about that on Friday.
But you can't tell which direction.
Well, you can't tell which direction. You can, in theory, get a sense of shear if it's sort of, push on the base versus pull from above. It's a tricky observation. But I think there are, observations of anisotropy definitely bear on this problem.
Very exciting. That's a very exciting area of new research, is this idea of getting shearwave anisotropy at depth, so you can start to put together more powerful arguments. So I'm going to move on, if you guys will let me, although I'm very tempted to stay here, but as you'll see, I'm less than halfway through my lecture, and I did want Pauline to make her appearance. Pauline decides against a career in business there, so we all sort of feel like that, but... All right, so let's talk about how planets cool off, sort of change gears a little bit. And here we have the five planets that we understand, and we promote the moon to be a planet because it's almost the size of Mercury. Absolutely, one of the most exciting things that happened in the last few years has been this mission to Mercury and some of the surprises that it's developed. But Mars is absolutely an attractor for all kinds of research. Venus is, I hope we start to understand Venus better, because Venus is our twin. And when the Magellan mission started, they fully expected to find plate tectonics on our twin. And one of the disappointments to parts of the community was that it doesn't have plate tectonics. So let's just talk about how these planets cool off, because if you think about plate tectonics, it's just a way of cooling off the planet. It's a special way, it's a remarkable way, and as our small sampling shows us, it's a very unusual way. But in terms of understanding Earth history, if we looked at those five planets and all of them had plate tectonics, we'd say, hey, that plate tectonics, that's what silicate planets do. And if you look at five and only one of them has plate tectonics, maybe you go, well, maybe plate tectonics is unusual in space, and it's also unusual in time. So things get a little more interesting when we can bring the other, our neighbors into the game. Part of the problem is that 60% of our, or 40% of our sample are not doing anything, really. They're just dead. So the moon and Mercury are both tectonically dead. Certainly they're cooling off or heating up or whatever they're doing. But they're not having any magmatic activity. They're not having any significant deformation other than when something collides with them. Mars, Venus, and Earth, on the other hand, the larger ones, still have enough energy to put on a show, to erupt once in a while, to deform once in a while. So obviously you have to have this size filter in order to use these. So these last three, Mars, Venus, and Earth, give us some idea of how do planets cool off? How do planets get dead? So one of the concepts that came out of Venus was this concept of the stagnant lid. So we have plate tectonics. This is from Koronaga's very recent summary of plate tectonics. When did plate tectonics begin in annual reviews of Earth and planetary sciences? And for the junior Siderites, if there's one place to go to try and keep up with our science, look at annual reviews. They always have the big areas identified. There's always something interesting in there that provides you an up-to-date overview. If I had just one thing to read, it would be annual reviews. But anyway, Koronaga's Cornaga considered plate tectonics, which we know and love, and then we have this thing called stagnant lid. And what stagnant lid is, in both cases we have this conductive layer. We call it's the lithosphere, and underlain by a convecting layer. And the difference is that Earth and plate tectonics, that conducting layer is moving, whereas in these other two planets, as we'll see, Venus and Mars, the conducting layer just sits there on top, doesn't move. Well, it ruptures, magma comes up through it, but it doesn't translate horizontally. We could put all the GPS there we wanted to, and we would be getting, still not doing anything. But this stagnant lid mode of cooling is very interesting for a number of reasons. So we'll talk a little bit about them. Let's just take a look at one of the stagnant lid planets. This is one of my favorites, is because, looking back at how we saw reality, we can see things where we go, how could we be so blind, as to draw these lines on here? Well, there was some relationship to some of these lines. I'm not sure exactly which of Lowell's canals would line up with the Valles Marineris, but it is remarkable looking back at what our maps look like compared to what we think they are today. Mars is everybody knows it's got the largest volcano in the solar system, and this is something like what happens when you have reasonably low gravity and a mantle plume or some mantle instability that just keeps pumping away. It just makes these big volcanoes of the Tharsis region. It's one of the characteristics of Martian geology is these big constructions that don't move anywhere. Obviously, there's a lithospheric strength issue behind the size of the Martian volcanoes, but this is one manifestation of stagnant lid planet. There's no plate tectonics on Mars, and things are behaving like that. Venus is the other one. One of the remarkable accomplishments of the late 20th century was the mapping of the Venusian surface with the Magellan spacecraft. And basically you've got all of these highs and lows. The reds are the highs and the blues are the lows. And one of the arguments is that what you're seeing in Venus is a periodic resurfacing. So every 300 to 500 million years, this is a very flexible interpretation because it's based on crater counting, and the Venusian atmosphere is so dense that the big crater, that most meteorites burn up, and then any impact is likely to get covered over with basalt. So the age of these surfaces are difficult to understand, but an understanding of this stagnant lid planet is that periodically it resurfaces itself. And we can think about why that happens. Yeah.
This may be really naive, but it seems like actually the analogy between Venus and Earth isn't super great because we can put things pretty far in the Earth before they vaporize. And we can't even get through the atmosphere in Venus. And so really you would be doing a lot of the cooling at the top of the atmosphere, right? So then it should act more like a gas giant, really, in a way, with a very big core.
Yeah, and that's a hydrodynamic question, which is way out of my comfort zone. Obviously, there's huge differences, and one of the big ones is the density of the atmosphere and the temperature at the surface, which is ultimately controlled by that CO2 atmosphere. So yeah, those of us that are geologists, there's some planets that geologists are very comfortable talking about, Mars being the most. We love talking about Mars because, we look at that, there's sediments, or that's a rift, or whatever. This planet makes us a little nervous. It doesn't make us as nervous as Jupiter does. And Jupiter's like, do we have to talk about Jupiter? We have no intuition whatsoever. Other than their hurricanes. We like their hurricanes.
Just one thing.
Yeah.
Relative to the atmosphere. With planetary signs and sometimes like the Earth, what we see is now. We don't know when that atmosphere kicked in. It relates to when did the runaway greenhouse effect kick in on Venus. That's what the S mission is trying to figure out. But I will tell you, there are models that say right after formation, and there are models that say around that 500 million year time.
Cool. So this is Phillips and Hansen's model for Venusian tectonics. And it's stagnant lid, but it's an active stagnant lid. And this is sort of the first order separation I would make in stagnant lid tectonics is you've got dead stagnant lid like the Moon and Mercury, I think. I don't really know much about Mercury, just what I read in the papers. But Venus has got this very active stagnant lid. So right there you've got a separation in stagnant lid tectonics. And the idea is that you've got mantle plumes, they're heated by the core the way we know and love. And then you also have delamination, that the base of the lithosphere sinks, and maybe that's what's causing if these 300 to 500 million year resurfacing events happen, maybe these things are all linked somehow, that the plumes come up, the lithosphere collapses, and you get a big resurfacing event. I don't know. So let's move on. So let's talk about why do we care. Obviously, it's interesting, these discussions about what moves the plates and what other ways of cooling the planet Earth could have experienced if it didn't have plate tectonics. But from the point of view of what we're trying to accomplish here in CIDR, understanding the continental crust, what difference does it make when plate tectonics began? Well, plate tectonics makes crust today. One of the magmatic expressions of plate tectonics is the formation of crust. And Earth is unusual because we have two kinds of crust. We have oceanic crust and we have continental crust. Continental crust is the topic of particular interest here. And where does plate tectonics make continental crust today? At convergent plate margins. Now, some people will argue that hot spots, oceanic plateaus, especially the initial outburst of when a mantle plume arrives at the surface, generates material that gets added to the continents, and they use the example of Wrangellia in the Pacific Northwest as a spectacular example of that. But most people who have thought about how plate tectonics makes continental crust would agree that most, what do we mean by that? Most of the continental crust today is being generated at convergent plate margins. Island arcs, the Sierra and batholith over here on the other side of Fresno. That's where it happens. And this region of crust formation is incredibly complex. So what we see is, down here at depth, we have the subduction factory, and next week I'll talk a little bit about subduction, but basically you have circulating asthenosphere and hydrous melting, and those melts, the mantle seems to like making this thing basalt. Those hydrous basalts come up, and because plate tectonics, convergent plate boundaries stay in the same place, the locus of igneous activity stays in the same places. In the mid-ocean ridges, the igneous activity, you have an igneous event, but then it gets carried away, so you never get much of a vertical construction. You get that with plumes, but they move away too. Hawaii, keeps moving away. In these arcs, the plate keeps going down, the material keeps getting added, and you thermally work this crust as you thicken it. So that's the main thing that processes this deeper crustal material, is the fact that this region is heated up, magma heat, and it goes on for 50 or 100 million years, incredibly long periods of magmatic additions, the crustal filter acting and causing fractionation and anatexis, and that's one of the key arguments about how we make the continental crust is what's making this unusual rock type called granite. It's probably not found on any other planet. Granite seems to be the signature rock of Earth. How is it generated? Is it generated by fractionation or anatexis? Melting of pre-existing rocks, crystal fractionation of melts from the mantle. Doesn't matter. All of this ends up being created, and then this somehow is the nursery of continental crust today. Yeah, yeah.
Can I ask more a general question? So you say most of the continental crust today is being formed at subduction zones. And just as a crazy question, and you said water, what if there was not much water? Can you still generate arcs?
That's an interesting thought experiment and a topic of.
No, I'm talking about you have the background water in the mantle, 2 inch ppm, but we're talking excess water down with the wedge. So you still have plate tectonics, you still have subduction. Could you get arcs?
And I suspect.
I mean, most people are going to say no, but I don't know if that's.
I'd rather not take a position. It's an interesting question that's worth further exploration. I mean, so the question really is, can you generate felsic rocks without water, right? So,
Without a lot of water.
what's a,
Or actually, back to reverters, I mean, this may be a big question. Do we really need water to have plate tectonics?
and that's a very good question. I think that'll be a question that a comment that when it comes down to why are Venus and Earth so different, it'll be one's the water planet and one's the CO2 planet. Yes.
I'll just point out again that there are felsic rocks that are generated in non-arc settings, which is nice. They're volumetrically minor, but they exist. There is a little water there, I think, because they also have ample. So
10% of oceanic crust is plagiogranite.
sorry.
10% of oceanic crust is plagiogranite. That's
Granites are 10%.
10%. Where does 10% go
Yeah.
down? What is that?
Well, I think that's the estimate that I got from
That's pretty high.
Yeah, yeah, I would contest that too, but.
Granites aren't actually that common in arcs, actually.
Well, true granites are not, and now we start to go into the petrologic zoo. Granitic rocks are common. True granites are not, absolutely. So this is an interesting point of discussion. I mean, here is the sort of thing that would make continental crust today, and these are natural laboratories, tremendous opportunities for petrologic research to understand this thing. It's a cartoon. So let's talk about lost continents, because we mostly focus on the fact that continental crust is created at convergent margins, and we less commonly explore the idea that continental crust is destroyed at convergent plate margins. And it's not quite as exciting as this particular movie. We may have to wait a while longer for the realistic Lost Continent movie to come out. So I just want to give you 3 sort of plot devices that we could use in this movie. One of them is the truncation of North America about 250 million years ago. The geology of this part of the world is dominated by a craton in west of sort of Idaho and coming down actually to Los Angeles, and then a passive continental margin shelf that's been tectonically worked, sort of dominating Idaho and Nevada, and a little bit of an island arc up here in northern California. All of these trends have been cut off. And we know when it was cut off because the first inklings of the Sierran batholith starts in the Triassic, and there was a new trend developed beginning at the beginning of the Mesozoic along here. What no one has ever figured out is where the hell, well, A, how much of stuff was lost from North America, and B, where the hell it went. One very likely possibility is it went down a subduction zone, that it was sheared off during the opening of Tethys, which in this part of the world we most firmly relate to the opening of the Gulf of Mexico, but that opening event was accompanied by a shear margin along western North America. Jason Salibi has demonstrated this convincingly, that there was a shear margin here in Permo-Triassic times that sheared this stuff away, and it went somewhere down the tubes. Okay. Maybe you don't believe it? Okay. Plot device number 2, the subduction of Arabia since 20 million years ago. So geologists have argued that Arabia contacted Eurasia, the beginning of collision perhaps, about 20 million years ago. plate motions reconstructed as best as geologists and geodesists can do show that there's been no change in plate motion of Arabia with respect to Eurasia over those 20 million years. So Arabia continues to be subducted beneath Eurasia. And we had a very interesting discussion at the end of yesterday about this, and some of you may find this plot device less convincing than other, but okay, it's something to think about. Continental crust, we have this sense that continental crust is unsubductible, but that's demonstrably false from the third argument, which are ultra-high pressure metamorphic rocks. One of the most exciting things that happened in the last 20 years was the recognition that continental materials have been carried down to 100 kilometers or more, and the diagnostic thing is the diamond seam in zircon, so the Kokchatev Massif in Kazakhstan is the most spectacular example of that. So there's the diamond stability field goes like that. So it's got to come down to at least 2 or 3 gigapascals, so a couple 100 kilometers at least. We don't know how much more. The other argument is coesite in quartz. So coesite, that could be a little bit lower pressure, but very strong indications that continental materials are carried down and then come back up. I mean, why? And once you're down to 100 kilometers, you should be, we shouldn't see you again. But so there's a very interesting poster out there about how these materials come up. I invite you to take a look at it. Okay, so they're just, we can argue about how much continental crust goes down, but there's proof that some of it goes down. Whether Arabia is going to be somehow turned into a big ultra-high pressure metamorphic terrain. All right, so we tried to put together a budget, and this is a very useful exercise because it exposes our ignorance. The best exercises are the ones that make you say, we need to study that. So there's been 3 efforts in the last few years. Dave Scholl and I did this in 2010. And so these are the things that add continental crust. And the units that are being shown here are Armstrong units. So this is a Bob Kay honoring of Dick Armstrong, who argued against vociferous opposition 20 years ago before he died that continental crust is being recycled. And in honor of that, Bob Kay said, let's call the 1 cubic kilometer of either production or destruction the Armstrong unit. So 1 cubic kilometer, that's what these units are. So as best as we can work it out, this is what is added to the continental crust each year. 2/10. Now these are 2 different estimates. One is by myself and Dave Scholl, and the other is, the one in italics, is Peter Cliff. So that gives you some idea of how much we agree and disagree. And he actually did it before we did. Didn't really know about that paper when we did it. But continental arcs, arc magmatism out in the ocean basins, there's a difference of 50% estimate. And then these are the losses. So things that are lost by sediment subduction, big difference of opinion. Subduction erosion, which is the overriding. Oh, yes.
Please provide us some uncertainty on these numbers.
We're very uncertain.
Just outside my field, and I would say that I have 0 idea as to whether or not 0.2 has a plus or minus of 10 or 100.
Well,
I don't mean percent.
no, I take your question seriously, and the only answer I can give you is one that exposes our ignorance of these issues. And how do you deal with the admission of ignorance, except with humor? So, I can't. I'd love to. We as a community should. Each of these represent stabs in the dark. We have more uncertainty about different ones of these than others. The delamination flux is a particularly perplexing one. Some of us will put a number there. So I think Peter Cliff was willing to put a number on the delamination flux. I'm so uncomfortable with estimating even an order of magnitude that I can't do that. I guess, I'm sorry. I can't give you an uncertainty. This is an opportunity for the junior siderites to say, let's try and do that. Let's take one of these and try and nail the uncertainty and get serious about this game. This is a cartoon. This is a cartoon with numbers. The worst cartoons are the cartoons with numbers, so you're absolutely right. But, I mean, this is where we are.
So could you tell me why Stern and then another Stern?
Charlie, no relation.
Have come out with 2 significant and then 3 significant figures?
We're geologists. we don't really pay attention to significant figures as much as we should. It's certainly a problem for my students. I know. I don't know, maybe a problem for yours too, or to a greater or lesser extent. And I'm not comfortable with much beyond 1 significant digit. Absolutely, you're right.
I don't know if it's worth mentioning, but some of these do have uncertainty. Subduction erosion from the Clue study originally. I mean, that's coming from seismic reflection and things like that.
Good point.
That one's got a good uncertainty to it, if we want to put those papers up.
Mm-hmm.
So, the subduction erosion one, I think that's plus or minus in the 0.1.
Yeah.
Maybe jumping ahead slightly, but what it seems like these studies are indicating is that we have a net constant balance of continent because we're removing and adding about the same amount. So doesn't that get back to the question of why do we have like these really super stable arcane cratons?
Yes, it implicates a lot of things. You're absolutely right that once you start throwing these numbers up there, the thing that jumps out as you is, well, we're not real sure on the total budget. The big question is there more continental crust being added or subtracted? That's a question that these differences between, Clift is arguing that there's the total crustal losses approach 5 Armstrong units. Dave and I argued that it was greater than 3.2 because we couldn't put a number on what's called lower crustal foundering, but more commonly used is the term delamination. I don't like that because it implies that there's a lamina, and the lamina is somehow peeling away like wet wallboard or something, and probably the real losses, if they occur, are sort of Rayleigh-Taylor instabilities. So rather than link a particular description of how that happens to, I just call it foundering, and then we can discuss mechanisms as well as fluxes later. But yeah, that's what I would be excited about if the junior siderites said, hey, wait a minute, maybe we should consider crustal losses as much as crustal gains. Sinti.
Along those lines, Rick and Kent showed all these images of crustal ages being very episodic. So this is clearly a snapshot of today, even. I don't know. But maybe it's better to look at portions of these because the absolute numbers or fluxes can be changing through time. And with proportions, you can do it by mass balance instead and compositional. And that might be a way forward to refine these.
Yeah, no, and the supercontinent cycle makes you think about, okay, how would these things vary over a supercontinent cycle? Once we did finally come up with some confidence in our numbers, or then we could say, okay, the supercontinent cycle begins with rifting and then ends with collision, and if we really do lose continental crust in subduction zones, then you'd expect the crustal losses to happen more at the end of a supercontinent cycle than the beginning. So there is a time element that has to be considered that isn't considered in this cartoon. This one just is trying to capture what the main losses and gains are and how we agree or disagree about what they are. And I think you can see that this is a very fertile ground for people that want to play this game, and I think it's I mean, really, that's one of the first questions we have to ask about continental crust is it growing or shrinking? Yes? Can we do that sort of offline and maybe as a group that, because the first thing I have to do is reread our paper. One of the things that happens as you get older is your memory sort of goes, yeah. Is it back then?
Yeah, I just wondered if these additions were sort of what you might consider juvenile additions, or whether it's taking into account and Texas or recycling already translated.
No, that we were trying to identify juvenile, that if you're recycling existing crust, and I think people have made the argument that the best place to make continental crust is at an Andean-type margin. That's, the only part of the Andes that we would like to know about would be the addition from the mantle, not the remelting of pre-existing crustal rocks. That doesn't get into this budget. It's sort of, in the university, the money goes from the academic departments to the physical plant. It's not the same as when you have to pay for a service outside kind of recycling. Yeah, Rick.
One observation that's not involved in these calculations, I think, should be is the effect of recycled content on mantle composition. So if you think about the level of incompatible enrichment of the continental crust, 1/10 of a weight percent of that mixed into the mantle will take the barium-niobium ratio, the 87-86 strontium of that mixture of the mantle outside the range you see in interplate oceanic basalts. So what that means is if you're recycling these quantities of crust, you have to do it in a way that by the time it goes through the whole mantle circulation system, comes back to the surface, it's been diluted by thousands to one by mixing with large blocks of mantle. I think that's a problem.
And my addendum to that would be over what period of time? We're talking about the plate tectonic the effects of plate tectonics on continental crustal growth and destruction. And you're right, we have a signal, an older signal coming from the mantle. But if I say that plate tectonics has been doing this for a short period of time, your objection would lessen. Yes?
Just a comment on that. What Rick just said is that I think you're talking about something like upper continental crust, and we're talking about mafic material. It's not quite as big a problem as it would be for sediments.
Yeah, I mean, gloss
yes.
would be an example for the numbers I was talking about. So an average subducted sediment.
But the stuff that you see in ultra-high pressure metamorphic rocks, that getting mixed into a mantle reservoir should have a significant effect. And most of the ultra-high pressure metamorphic rocks, they have to have quartz or they've got diamond, which means they've been in a carbon-rich environment. So they probably were upper crustal materials. But
they came back up.
Yeah.
We don't know what proportion.
Yes, that's right.
Yeah, I think one of the great uncertainties is how well the mantle is mixed. We're going to recycle this stuff down there. Rick is right. If it's mixed in the whole mantle, you've got a problem. But if it stays in discrete areas and plates here and there that accumulate to double prime, it is not well mixed back in the majority of the mantle. That eliminates at least some of that problem.
Yeah.
So just a quick comment. Maybe another number actually will be relevant here. And the present day production rate for the oceanic crust is about 3 AU. I mean, first time I see you this unit. So I mean that's the present day production rate for oceanic crust, 3 AU.
No, I think it's high. I think the oceanic crust is on the order of 20.
No, 3. I wasn't so sure. I just checked.
All right. Okay.
So both you have 15 minutes.
Oh, okay. Well, I was hoping this would happen, so yes.
Okay, a bit about how do you obtain these numbers? For example, how do you estimate the lower class boundary?
I was proud. I was proud because the one thing a scientist wants to do is put numbers up there. And Dave and I said, we can't with a straight face defend them. And what you've just done is, those are our question marks. You basically validated my lack of courage, which was like, I can't defend that, so I'm not going to put a number.
About the subduction zone, you have some sediment that go in subduction and other sediment that go to form the prism.
Mm-hmm.
So how can you estimate these two?
Well, there's a literature, and I'm not. So I have 15 minutes, but you haven't asked a question, so please.
The same line. Is there a hope to estimate lower cross-foundering then?
I hope that some of the junior siderites will show a way to move in this direction. I think this would be a great contribution if we thought about how we could spin off a project off of this cartoon. That would be one. That would be another. So 10 minutes now, huh? But that's fine. That's what I was hoping would happen. So have you guys seen these kinds of diagrams before? Okay. Okay. Well, so I want to throw. I'm glad I got to this point because what I want to do is show you that. And this is the range of crustal growth curves that has been shown with, great diligence by. So that's Earth history 4 billion years ago, the age of the oldest crust. Another one to do it would be to consider the oops, now I'm coming apart. That the crust once covered the whole planet, and what we're left with is about 7.2 times 10 to the 9th cubic kilometers cubed. That's the continental crust volume. And that we've been losing it with the beginning of plate tectonics at something on the order of 2.6 Armstrong units per year. That's, reasonable given the uncertainties in what plate tectonics does. Remember, that crustal growth curve is just the rocks that are still here. What if the crust is disappearing? Those curves mean nothing about crustal growth. They only mean what is preserved.
At first order, wouldn't you think that the loss was somehow proportional to how much was there?
No, I think it's proportional to the
At the very, very beginning, you just had a teeny bit.
That's
we could lose the 2.6.
All planets, silicate planets, have crusts. And so what we see is the Earth is the only one with the bimodal crust, continental and oceanic. So one perspective, and the dominant perspective, is that crust has grown with time in some way or another. But another equally valid position, and I'm glad to get to this point because this is a challenge I'm happy to take, is that the planet was originally covered in continental crust and has been losing it. And tell me why that is the most ridiculous thing you've ever heard. Isotopically, I know what you're going to say, but
there's another issue with it. So right now, the continents have half the uranium in the Earth, and if they're 3 times their present size, they have more uranium than the Earth has. So they can't.
They're the same composition.
They can't be the same composition they are now and be 3 times their volume, their current volume. So. Basically, you'd have to push them back into being a basaltic crust, in which case you're talking about losing, Hadean basaltic crust is fine. We'd lose, Cenozoic basaltic crust.
But what if that uranium has been processed through multiple episodes? It keeps going down, but it keeps coming up.
But you're talking about removing it from the Earth's surface.
Yeah, but things like potassium and rubidium, cesium, uranium, they're going to find their way back to the surface. Preferentially.
Yeah, they're called continental crust.
Okay. So, anyway, it's just a little, maybe that'll open up a little imagination space that in trying to assess the significance of these curves, that the realm of possibilities might be a little bit larger. So that's for the junior siderites as much as anybody. Yes?
So what would be the mechanism for giving you the primitive Earth that's all continental crust?
No, but none of that crust is here. So we're talking. So as a geologist, what I really want is a sample. And with a sample, I can get data and I can make an interpretation. We don't have any samples. We've got these wonderful zircons that have inclusions that have been perhaps overinterpreted, but they are the piece of that early history that we have to work with. The rocks themselves.
No idea.
Yeah. Thank you.
since you brought up other planets, you said they all have continental crust.
No, they all have a early. They all have an early.
So we do have samples of the crust.
Yes.
And it's not continental, as best we can tell on Venus. And so Rick's argument, I would say, is right. I mean, if you say the early stuff you're talking about is something the salt like that got reworked and built up, then I will agree with you. I can't argue against this. I thought I could. I tried. I can't. However, if you are saying it's granitic, then I think you have some problems.
Well, I've got to bring this to somehow a halt. I'm about halfway through the talk. It's because you guys had so many questions, which is in this kind of a setting, what I hoped was that I wouldn't make it anywhere close to the end. I've succeeded far beyond my wildest dreams. But the point in that I'm not going to get to is discussing when plate tectonics began. But a key piece of that understanding is the understanding that continental crust is as much destroyed by plate tectonics as created. And I did get to that point, and with that, I'm pretty happy. Richard, you'd be best. I mean, I can stop there. I can go on a few more slides. There's questions. What would you...
Why don't you give us the 2-minute synopsis on when you think plate tectonics started? Or something like that.
That was my question.
2 minutes.
2 minutes, given uncertainties as Bill has just outlined.
Okay, is that... Sure. It's not going to be 2 minutes, but I'm... So, okay, I'll just zoom through the rest, the slides. Well, I like the cartoons, so I hate to zoom through those. And the Urey ratio, which is a great thing to talk about because Harold Urey got his PhD here. What a wonderful story. And stagnant lid, and evidence for a shutdown, delamination, foundering. Okay. We can theorize till the cows come home. What do the rocks say? So this is where everybody in this room has an opportunity. Open up your minds to the possibility that plate tectonics hasn't always been going on this planet. That's almost assuredly true. And if you read Korenaga's paper, he has a very nice stratigraphic column of what the people that have taken a position on it in print say. And I am way up there towards the top. I think it's Neoproterozoic, and most people put it in the Archean. But let me explain to you why. Because I think, we can't just rely on the models. We have to say to the modelers, here are what we see the constraints are. So we could talk about the petrotectonic indicators that are diagnostic of plate tectonics and go in and interrogate the planet and say, when did these rocks get produced? And there's several of them. So there's general plate tectonic indicator, which is ophiolites. Everybody knows what an ophiolite is. Anybody not? Happy to explain. It's one of my favorite rocks. Should be the state assemblage of California. Subduction indicators. Jadeite is a metamorphic mineral that's associated with subduction zones. Blue schists, glaucophane schists, another candidate for the state mineral of state rock of California. Lawsonite eclogites, a sort of a subvariety of eclogites. Those are shown there as a function of time. So,
would it be possible to normalize that by the amount of exposure of the different ages?
Sure. I think that could be done. Yeah, different. But there's lots of old rocks running around. I mean, Australia, South Africa.
Yeah, but not nearly as much as there are new rocks.
Yes, but still, if there was a proportionate distribution of blue schists through the geologic time, and Kent will correct me, there would be a lot of bars sticking up here. Is that a fair statement?
Fair.
Okay. And then collision indicators. Subduction is, these are two different types of plate convergence, but because subduction is fundamentally different, sort of healthy plate convergence, and continental collision is pathological plate convergence. You have different indicators. One of the most spectacular, of course, are the ultra-high pressure metamorphic rocks, which don't appear until about 650 million years ago. Ruby, in particular, is a metamorphic gem. This is from a paper we just published in Geology, talking about plate tectonic gemstones, ruby and jade. And you see that these, what we find as very powerful plate petrotectonic indicators of plate tectonics: ophiolites, jade, blue schist, lawsonite eclogites, ruby, UHP rocks. Continental margins I'm not going to talk about because this is much more interpretation driven. They all start in the Neoproterozoic. So I think I can leave with the comment to the junior siderites in particular: find the thing that is the most convincing to you of plate tectonics. It could be isotopes. Some people find that the evidence that there was a circulation from the surface to the interior of the Earth from the earliest time of Earth history convinces them that plate tectonics began at that time. I don't find that. I think there's other ways to take surface materials to depth, but you need to decide for yourself, what do you find interesting, convincing about the indicators of plate tectonics. And with that information, construct, defend, argue about a history of when plate tectonics began. To me, this is one of the most exciting opportunities in the solid earth sciences, is to start to go after the history of our planet. And it's really exciting because in this fantastic search for exoplanets, people are looking for other people out there. And one of the things that is clearly critical is life. You need to have life on a planet. Somehow the one planet in our solar system with life has got plate tectonics. Is there some kind of a relationship between how we got where we are today and when our planet started doing this unusual way of losing heat? And I think probably I ought to stop there. Huh? So
on the off chance anybody didn't get to ask their question, we can take a few more questions right now.
I'll just mention there's a couple of possible datums that are not on your plot there. One is that there's been a proposed ophiolite at 2.5 billion years in North China Craton. It's highly controversial, but Tim Kusky and his co-workers have proposed that. The other is that you may not be aware of this work, but Pierre Cartigny studied some diamonds from a kimberlite that I think is 2 billion years old, and said that these were UHP diamonds from continental crust. So if that would put those back to 2 billion, if it's correct interpretation.
Mike Brown doesn't believe that at all. I've talked to him about that.
Yeah, I know. I'm the one who told him about it, and he doesn't believe it because he wants plate tectonics not to be operating in the Archean.
So, but I have to comment on the Archean ophiolite because there have been two papers in Science. One of them, the North China Craton, the other in Greenland, the Isua Belt. Both of them have been challenged, and I think convincingly so. Not just because I'm happy to see them disappear, but I think the scientific community that's looked into this has said, nah.
Bob, another way of looking at this is if you just look at erosion rates, there are about 5 of your Armstrong units a year. And probably 75 or 80% of that is recycled sediment and doesn't really come into the thing. But, if that's the case, then you've got maybe roughly a cubic kilometer approximately, 1 Armstrong unit of erosion of, kind of real crust. And then that implies a very long residence time for the crust that remains to be processed through that. So if you want to sort of erode crust and then subduct some of that and then some even smaller fraction, I mean, that's a residence time longer than the age of the Earth, right? So I'm not sure, what that gets you, because it would imply that much of that crust must be stable for longer, have a expected lifetime longer than the age of the Earth. And that's not necessarily really what we observe in the geochronology, right? We don't have lots of 4 billion year old terrains out there. We have a few, but I'm just kind of, that's an argument there that I think is telling you something about the dynamics of that recycling.
Anybody else?
Greg?
So one thing that is kind of a fun puzzle is to ask in the kind of models that you talked about of the formation of crust and the evolution of the Earth and Uri number, all of this. What kind of rocks would you expect if the Earth was a little hotter? Would you make blue schists, or would the blue schists be something else? Would they be green schists? Or
that's a really good question. So one of the arguments, the blue schist observation has been around since before plate tectonics. This was people talked about the fact that there was no blue schist in the Precambrian. Well, they found some, but it only goes back to about 800 million years. So one of the arguments is, well, the Earth was hotter, so the thermal pressure conditions weren't conducive to forming blue schists. Now, this brings up the question of how do blue schists form? Blue schists form in subduction zones. Subduction zones represent regions where a huge tracts of lithosphere are injected. Cold material is injected into hot mantle. And geodynamicists have shown us convincingly that the thermal structure of a subduction zone, to the most part, is controlled by the thermal parameter, the convergence rate times the age of the oceanic lithosphere being subducted. At the slab surface is controlled by the temperature of the ambient mantle. Most of the estimates for Earth's ambient mantle are maybe a couple hundred degrees hotter. People have done this using SINTE's geothermometer for basalts back into the Archean, and they're not that much. Komatiites you have to have a hotter Earth, but it's not 1,000 degrees hotter. So you have a modestly or moderately hotter mantle, but the main thermal control on subduction zone is that material that's being injected. So, and in fact, if you think about the thickness of the oceanic crust, blue schists are mostly subducted oceanic crust. You've got a thicker pile of oceanic crust to turn into blue schist. So it's actually should be more favorable for the formation of blue schists in the past than at present. That's sort of taking an extreme argument, but the simple statement that the Earth was hotter, therefore there were no blue schists, is misleading because blue schists don't reflect the temperature of Earth's mantle. They represent the temperature in the oceanic crust, a kilometer, 2 kilometers below the slab interface in the subducted oceanic crust. So that would be my response to people's argument that blue schists, you don't see blue schists because Earth was hotter. Yes?
How are they returned to the surface?
Yes, good question. I think SINTE's and his students' poster out here shows that very nicely, that there's two arguments. One is that it comes back up the subduction channel, which is something Mark Kloos worked out for the Franciscan here, that somehow there's this elevator that goes like that, and the Franciscan is the most spectacular example of that subduction channel thing. And the other is that these things develop as low-density diapirs above the slab interface, and then they organize and rise diapirically. I think those are. Is that a fair statement, Sinti? That it's got to be somewhere between those two possibilities.
Ask Monica.
Monica? Where's Monica?
Yeah, those are the two arguments.
Would you add anything to my simple-minded?
No.
Okay. Diapirs and subduction channel.
But that might be another interpretation, is somehow the aspect of those return mechanisms could be somehow a little different.
Yes,
Certainly.
I'm going to suggest tomorrow in my talk a different way to do that.
Yes, and advertising, Kent Condi will give you a very different interpretation tomorrow. So.
Okay, I think we should stop there so we can have some coffee. Plenty of time to continue the conversation afterwards. Okay, let's thank Kurt again.
Thank you.
Great. So I think without
Thank you.